So an obvious property of the trig functions is that they're periodic. So if we're dealing with complex numbers, are cos and sine still periodic, and do they still have period 2 pi? And the answer is yes. This is fairly easy to see from here. If I put z plus 2 pi in, replace the z by z plus 2 pi, well, the 2 pi is obviously real, so it just affects the x bit. So that if I got z plus 2 pi, then I get x plus 2 pi here, and I get x plus 2 pi here. Now, cos of x plus 2 pi is the same as cos of x, and sine of x plus 2 pi is the same as sine x. So this expression doesn't change. And similarly with sine z. Sine z of 2 plus sine z plus 2 pi is the same as sine z. Now, you might not have heard that in fact the hyperbolic functions are also periodic. They're periodic with imaginary period. So cos of z plus 2 pi I is equal to cos z, and sine of z plus 2 pi I is sine z. So they have period 2 pi I. Again, this is easy to see from here. You've got cos of z plus 2 pi I. Now the 2 pi I, the 2 pi of that will go inside the y. So we get y plus 2 pi and y plus 2 pi. Obviously sine of y plus 2 pi is sine of y, and cos of y plus 2 pi is cos of y. So this doesn't change if I put a plus 2 pi I. Similarly with this sine of z plus 2 pi I get sine of z. Likewise, tan. Okay, well, also this is another useful relation that, well, tan has period pi. Why is that? Well, it's basically because cos of z plus pi is equal to minus cos z. Okay, that's also straightforward to show because cos of x plus pi is equal to minus cos x, and sine of x plus pi is equal to minus sine x. So if you've got cos of x plus z plus pi, then that's equal to minus cos of z, and sine of z plus pi is equal to minus sine of z. So if you divide the two, the minus signs cancel, and you end up with tan of sine z plus pi is equal to tan of z. So tan still has period z as period pi. You can do the same with hyperbolic functions. It's straightforward to show, and this is a useful thing to remember. Cos of z plus pi I is minus cos of z. And similarly for sine. Divide both of these, and you end up with tanh of z plus pi I is equal to tanh of z. So tanh has a period pi I. The following are sometimes useful. Okay, if we want to know what the modulus squared of a trig or hyperbolic function is, okay, so modulus, well, for example, the modulus squared of cos z we can get from this squared plus this squared. Okay, it's the real parts squared plus the imaginary parts squared. So if you do a bit of algebra, you get cos squared times cos squared, and you've got sine squared and sine squared. So cos squared you can rewrite using this as 1 plus sine squared, and obviously the sine squared you can rewrite as 1 minus cos squared. So if you do the algebra, you end up with this expression here. So yes, this is sometimes useful, not amazingly useful for other things. Right, so the next bit is extremely important. So a value of z for which any function f of z is equal to 0 is called a 0 of f. Slightly confusing terminology, but that's just the way it is. So we want to find the zeros of cos z. Well, when z is real, we already know what the zeros of cos z are, hopefully, if you can remember them. They are correctly. They are z equals pi by 2 and z equals 3 pi by 2 and any odd multiple of pi by 2. The question is, if z is allowed to be anything on the complex plane, are there any other zeros? Seems unlikely, since we've shown that cos has to be periodic with period 2 pi. But okay, we can show it more rigorously. Okay, really from this allows us to show that the zeros we know about are the only zeros. So to find the zeros of cos z, okay, we set this is equal to 0. How can this be 0? Well, it can be 0 only if both cos x is 0 and sine y is 0. So x is real. So we already know when x is what values of x is going to give you cos x equals 0. To get this to be equal to 0, well, the only possibility is y is 0. Okay, which means that y is 0, then z is x plus iy. Z is a real number. So the zeros of cos are the ones we know about. They're all on the real axis. And by a similar technique with the others, we can show that cosh of z has zeros along the imaginary axis, and sine of z has zeros along the imaginary axis as well. Notice the relation between these, that cos has zeros at n plus a half pi along the real axis. Cosh, its sister function in the complex plane, has zeros. Looks almost the same, except you've got this extra factor of I here, and the same with sine and shine. Okay, so these zeros are going up the imaginary axis, and as are with shine, just as with cos and sine, they're going along the real axis. So, I mean, the reason for this is simply going back to this relationship here. Basically, you can swap things around by changing the argument to iz, from z to iz, and then cos turns into cosh and vice versa. Anyway, just to stress this, it's easy to remember the zeros of cosh or shine, since they are simply obtained by rotating the zeros of cos or sine by pi by 2 about the origin of the complex plane. Okay, so the final thing I want to do in this section is something that will be useful later on. Now, when you simplify fractions containing a complex denominator, so something below the divide sign, what you normally do is you multiply top and bottom by the complex conjugate. So that's what we did in the first section when we talked about dividing complex numbers, z1 by z2. The trick here was, okay, well, if this is a complex number, 1 plus I or something, then how can we deal with it? Well, we can turn it into a real thing on the bottom by multiplying top and bottom by the complex conjugate of z2, and that will definitely make this thing on the bottom real. Okay, but that's not the only way, and it's not necessarily it can be a slow way of doing things. There can be a quicker way, which we'll illustrate in the next example. So in this example, we're simplifying this expression here, e to the I a pi by 2 over 1 plus e to the I a pi. So look what we do. Okay, we've got a complex expression here. If we were to multiply top and bottom by the complex conjugate, we'd have quite a lot of algebra to do. Okay, we'd have to multiply top and bottom by 1 plus e to the minus I a pi. So there's another way. We can actually multiply top and bottom by this. Now, why are we doing that? Okay, we multiply top by e to the minus I a pi over 2. Well, we're doing that because if we do that, then can you see on the bottom we end up with this expression here. I'm a little worried. I've made a mistake. There's a misprint here. I've forgotten the. This should be divided by 2. Okay, it should be e to the I a pi divided by 2, shouldn't it? Yes. Okay, so that should be e to the I a pi divided by 2, and this should be divided by 2 as well. Otherwise, but then I recognize this as being simply cos, or it's actually 2 cos IA pi divided by 2. And 1 over cos is, I've got a factor of 2 here, which gives me this, and I've got 1 over cos, which is sec a pi by 2. So sorry about the missing divided by 2 here. Right, so now you can actually do question 5. Since question 5 comes immediately after this example 1.1, you can probably guess that you should use something like a similar technique to solve this problem here. Okay, so that will do for now.